In this video, we are going to look at another application of the Poisson distribution, using Poisson distribution to approximate the binomial distribution in the case of weak dependence. So let me describe what the application is. First of all, recall that the Poisson distribution with parameter lambda can be used to approximate the binomial distribution with parameters n and p, where lambda is np, and the approximation is going to be good when n is large and p is small. Recall that the binomial distribution requires the trials to be independent. Now, the Poisson distribution with parameter lambda can still be applied if the trials are not independent but are weakly dependent instead, and probability of success is p for each trial. Let me explain this by an example. Let's consider n men with n heads. So we have men 1, men 2, men 3, men n. So the men are labeled 1 through n, and their heads are also labeled from 1 to n. This should be capital N. The heads are gathered in one place and mixed up, and then each man gets a head randomly. So what it means is the following. Imagine that the men are standing in order 1 through n. Their heads are taken off, and then the heads are rearranged among the men, and that is the heads are, so that is we are taking a permutation of the heads. So for I equals to 1 up to cap n, we are going to define the ith trial in the following way. The ith trial has two outcomes, success and failure. Success means the ith man receives his own head. Failure means not s, and the number of trials is cap n. EI is the event that the ith man receives his own head. So that means it's the event that success occurs on the ith trial. What is the probability of EI? Notice that the probability of EI is the same as the probability of a success on the ith trial. In order to find the probability of EI, so that probability of the event that the ith man receives his own head. So after we permute or rearrange the heads among the men, what's the probability that the ith man gets his own head back? That is, the ith man gets the head number I. What's the probability that the ith man gets the ith head? So the question then is, how many permutations of the heads, or how many rearrangements of the heads are there where the such that the ith head is on the head of the ith man. So that means the ith head is fixed. and the remaining n minus 1 hats can be rearranged in any order. So the number of permutations of n hats where the ith hat is on the head of the ith person would be n minus 1 factorial, and the total number of permutations of n hats is cap n factorial, which then is equal to 1 divided by n. Let's now look at what's the probability of EI and EJ. So that means what's the probability that the ith man and the jth man receive their own hats. So if you look at this picture, what it means is that after we permute the hats, what's the probability that the ith and jth man keeps their hats? Well, so how many permutations of the hats are there where the ith man and the jth man keep their hats? Well, the remaining n minus 2 hats can be arranged in any order. So the number of ways that can happen is n minus 2 factorial and then divided by n factorial. This is equal to n minus 2 factorial n times n minus 1 times n minus 2 factorial, which is 1 over n times n minus 1. Now, what is the probability, conditional probability of EI given EJ? Well, what's the probability that the ith man keeps his hat given that the jth man keeps his hat after permuting the hats? Well, by definition is the probability of EI and EJ divided by the probability of EJ, and that's equal to 1 over n times n minus 1 over the probability of EI is 1 over n, so that's for any I. So for probability of EJ is 1 over n as well. So this is equal to 1 over n minus 1. So notice that the probability of EI is 1 over n, and the probability of EI given EJ is 1 over n minus 1. They are not the same. They are not the same, but they are pretty close to each other. So this implies that the events E1, E2, en are weakly dependent. So that implies E1, E2, en are weakly dependent. In other words, the trials are weakly dependent. Okay, so what we can do though is that we can say the following. Let x be the number of successes. Remember, there are cap and trials here. Then approximately x has Poisson distribution with parameter lambda equal to, well, there are cap and trials, and the probability of success is 1 over n, which is 1. So the lambda is 1 here. And so approximately the PMF of x, the probability that x is k, is then approximately e to the negative 1, e to the negative lambda times lambda to the k, which is 1 to the k, over k factorial, which is e to the negative 1 times 1 over k factorial. Now, if we want to find the probability that none of the men gets back own hat. Well, in terms of x, it's the probability that x is 0, and approximately we can then say approximately that probability is e to the negative 1 times 1 over k 1 over 0 factorial, which is e to the negative 1, and that's about 0.36788. Okay, so now so this is the this probability is an approximate probability. The question that you might want to ask is what is the exact value of the probability that x is 0. So we used Poisson approximation to calculate that probability, but what is it exactly? In order to answer that, first of all, I need to know a couple of probabilities. What's the probability that what's the probability of EI? Well, we calculated that to be 1 over n. What is the probability of I intersected with EJ? So if I take two of the events, so remember we have these events E1, we have for each I we have the event EI, so E1, E2 up to E cap n, and then if I take the two-way intersections of if I look at the two-way intersection of any of those events, the probability would be 1 over capital N times n minus 1. We did this calculation before. Now, what's the probability of EI1 intersected with EI2 intersected with EI3? where I1, I2, I3 are three numbers between 1 and cap n, distinct numbers. And this probability will be, well, let's think about it. We have n men, n caps or hats. The hats are permuted or rearranged among them, and what we are asking is what's the probability that the men I1, I2 and I3 keep their hats, and the remaining hats could be rearranged in any order. So how many ways the event EI1 intersect EI2 intersect EI3 can occur? Well, so what it means is that the men number I1, men number I2, men number I3, they all keep their heads. So the remaining caps or hats can be rearranged in any order. So that means there are cap n minus 3 factorial ways that the three men can keep their hats, and the total number of permutations of the n hats is cap n factorial, which is going to be 1 over n times n minus 1 times n minus 2. In fact, let me write that this is the same. The probability of EI intersect EJ is the same as n minus 2 factorial over n factorial, and the probability of EI is the same as n minus 1 factorial over n factorial. So let's just keep these values in terms of the factorials. Now you see the pattern here. So if I want to find the probability of EI1 intersected with EI2 intersected with EIR, so that means R of the men keep their hats. So the number of ways R of the men can keep their heads is the following. So that would mean the remaining hats can be rearranged in any order. So it is 1 over, so this is n minus r factorial, and so that's divided by the total number of rearrangements of n hats. Okay, so now we are ready to say what's the exact probability that x is 0. That's the same as 1 minus the probability that x is larger or equal to 1. this is equal to 1 minus the probability that x is larger or equal to 1. Notice that that's the same as the probability that x is greater than, so remember x is the number of successes, that is x is the number of men who keep their heads. So that means this would be the probability of probability that either man 1 keeps his head, or man 2 keeps his head, or man 3 keeps his head, and so on. So this is the probability of the union I going from 1 up to n of EI. And from now we're going to use the inclusion-exclusion principle and say that this is the, first of all, the summation I going from 1 to n probability of EI minus summation I less than j the probability of EI intersected with EJ. Remember, so we subtract the probabilities of two-way intersections, right? And then we add the probabilities of three-way intersections. And then minus dot 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 plus minus 1 to the r plus 1 summation I1 less than I2 less than dot 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 less than IR, the probability of R-way intersections, so that means EI1 intersected with EI2 intersected with dot 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 EIR plus dot dot dot, and the very last term would be negative 1 to the n plus 1 P of E1 intersected with E2 intersected with dot 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 E cap n. So this is simply by applying the inclusion-exclusion principle. Now we know all these probabilities, so let's plug them in. What we have then is 1 minus the summation over I going from 1 to cap n of 1 n minus 1 factorial over cap n factorial minus the summation I less than j n minus 2 factorial over n factorial plus the summation I1 less than I2 less than I3 n minus 3 factorial over n factorial plus dot 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 minus 1 to the r plus 1 summation I1 less than I2 less than dot 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 IR, and this would be n minus r factorial over n factorial plus dot 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 plus the last one is negative 1 to the cap n plus 1 1 over n factorial. Now at this point we need to do the following. So if you look at the first sum, how many summons do I have in the first sum? In the first sum we have basically n, we have n summons. So one way to think about it is n choose 1, and so I have n minus 1 factorial over n factorial minus the second sum. How many summons does it have? Well, the sum goes over all I less than j. So remember, I and j are positive integers between 1 and cap n. So basically the number of summons would be the number of ways we can pick a pair ij from the integers between 1 and n. So from the integers between 1 and n, there are cap n choose 2 ways of picking a pair of numbers I and j. So this would be n choose 2 times n minus 2 factorial divided by cap n factorial. The next number would be n choose 3, right, because the sum goes over all triple of numbers between 1 and cap n. So how many ways can I pick 3 distinct numbers between 1 and cap n? That's n choose 3. There are n choose 3 summons in the third sum, and each one is n minus 3 factorial over n factorial dot 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 the rth sum negative 1 to the r plus 1, and that can be, there are n choose r summons there. Each one is n minus r factorial over n factorial plus dot dot dot, and the last one is just 1 over n factorial. There is only one summand there. Now we need to do a little bit of algebra now. Write the binomial coefficients in terms of the factorials. If we do that, what we're going to obtain is the following. We are going to get 1 minus 1 over 2 factorial plus 1 over 3 factorial minus dot 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 minus 1 to the r plus 1 over r factorial plus dot 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 the last one is -1 to the n plus 1 times 1 over n factorial. So what we obtain then is the following. Because I have 1 minus that, so I can get rid of the brackets here. So if I do that, I get 1 over 2 factorial minus 1 over 3 factorial plus plus minus 1 to the r times 1 over r factorial plus minus 1 to the cap n over n factorial and this is equal to summation -1 to the n over n factorial, where n where n is gonna go from zero to cap n. I have to be a little bit careful. This would be 1 minus okay, so I'm going to keep 1 minus 1 plus 2 factorial. So then I can write this as sum n going from 0 to cap n, -1 to the n over n factorial. This would be equal to the summation n going from 0 to infinity, -1 to the n over n factorial minus the summation n greater than cap n minus 1 to the n over n factorial. Notice that the first sum is the power series representation of e to the -1. So we have e to the -1 minus the sum over n greater than cap n, -1 to the n over n factorial. So given that cap n is big, this quantity is approximately e to the -1. That's a given n is large enough. Okay, so so now we see that the exact probability is pretty close to the probability that we obtained by using Poisson distribution here. So that's the point of the entire problem. Okay, so we will extend. We will look at another example where we will see that So in this example, remember that the probability of success is the same for each trial. And in the next example, we'll see that that's also not required to use the Poisson approximation.